Welcome everybody. Welcome first to our distinguished guests from the Embassy of the Republic of Korea, Ambassador Dr. Kim Woo-shang and Mrs. Kwon Moon-young. From the Japanese Embassy, First Secretary for Science, Technology and Environment, Dr. Taro Ide. Alumni and members of the community, welcome. My name is Will Grant. I'm from the Australian National Centre for Public Awareness of Science down on the ANU campus downstairs. Today marks the first event of 2011 for the Stromlo lecture series as we celebrate a special year, the 100th anniversary of observing at Mt Stromlo. It was in 1911 that the Oddie telescope was first gifted to the Commonwealth Solar Observatory, the original Oddie dome being completed in September 1911 at a cost of $600. As part of Mt Stromlo's centenary and in preparation for Canberra's centenary in 2013, the university is seeking federal government support to restore the Oddie dome, recognising its national heritage value as the first Commonwealth building in the nation's capital. Mt Stromlo was to take its place in the international chain of observatories able to track and observe the sun, an international cooperation which included work being undertaken in the Smithsonian Institute in Washington, D.C. in 1909. Fitting that history, last week the ANU announced plans to develop an astronomy and space science museum here at Mt Stromlo in partnership with the Smithsonian's National Air and Space Museum. As part of the Mt Stromlo centenary celebrations, we're very pleased tonight to present a special presentation on space travel and space science research. Our three panelists for tonight's presentation are Dr. Yi Soyeon, Dr. Daniel Bayliss, and Associate Professor Charlie Lineweaver. And thank you to them all for giving nice little bows there. The way that tonight's session will run is we'll hear short presentations from each of the three panelists before opening up discussions up to questions from the audience and from the fellow panelists, and I hope that it'll be a lively discussion. We'll begin first with Dr. Yi Soyeon. Dr. Yi is a Korean astronaut and astronomer with the Korean Aerospace Research Institute, KARI. On the 8th of April 2008, she was launched into space on board Soyuz TMA-12 and returned to Earth aboard Soyuz TMA-11 on the 19th of April 2008, and as the Wikipedia page tells me, that's 10 days and 21 hours in space. Since returning, she's been working as a senior researcher at KARI, as well as acting as Korea's space ambassador. Dr. Yi.
Thank you. Thank you for giving me this kind of precious chance to talk with you, and thank you for the Korean Australian Foundation to invite me to the Australia, and I really want to celebrate Korea-Australia Friendship Year. Maybe this year is kind of, maybe you guys don't know about that, but this year is like that. And I'm not an astronomer, sorry about that. I'm an engineer, and I don't have any idea about astronomy at all, even though I'm an astronaut. Because some people have bias if she or if he is an astronaut, he or she should know about astronomy or something. But our space station is just above 400 kilometers, so still very near to the Earth, so not that far. Actually, space station is kind of like laboratory and a branch of the Earth, and then just 400 kilometers. You can imagine that if with your sphere, and then just stick on the Earth. And today we just have 10 minutes, so I want to show just a short notice. But one thing is that we could do that in space. Yeah. Even though I'm not a master of meditation, I could do that. And until high school, I played the taekwondo, but I always dreaming about flying kick, because whenever I saw the movie, Jackie Chan do the flying kick and some other Chinese masters do that, but I cannot do at all. But finally I can do it. And of course, I didn't go to the space only for doing those kind of activity. I went there as a representative of Korea. Maybe all you guys already know about Russia or NASA space program. They have a very long-term and stable and a continuous human spaceflight program. But Korea couldn't have those kind of big budget for the human spaceflight. But as a country who already developed science and technology, they want to expand their experiment or science and technology to the space. So we made a short-term project for making an astronaut, but not only for making an astronaut, but also for the start with a space experiment in station. So we made a contract with Russia, and we got one ticket to go to the space station and then stay 10 days. So my most important mission is doing the space experiment in the space. So I want to show you some activity as people who do the space experiment. Yep. And then I brought 18 experiments from the Earth to the station. And then we bring some fruit fly to see about DNA mutation or something kind of like behavior. And also bring some cells and to growing up and to culture in space station. And then also we have a puppy face in space. So take a photo. And here's a space kimchi. We develop a kimchi and rice to eat space. And you know, very famous Korean food. And also do some chemical experiment because there's no gravity. So all the crystal is growing very uniformly. So we do want to check that. And also bring some telescope to see above the Earth, and then we want to see above the atmosphere, so we brought that. And then also I have my own camera and I take a photo above the Earth, and then there's some place. But unfortunately, I've been there only 10 days, so I could meet the Korea several times, and then most of the time I should do experiments. So sorry about that. I couldn't wave to the Korean peoples above. And also we developed some mass measurement system because there's no weight. We cannot use the weight. And it's not a jello, it's a water. But there's no gravity, so they move like that. And also some performance for the kids. And here's a space. And this kind of experiment also. And then we have a campaign for the Powerful Korea or something. So I did a great time in space. And actually, I had one idea when I heard about his comment, and then all the ocean. Actually, you have a 100-year celebration for the telescope or something. But at the time, 1911, we Korean people had a really tough time. Even we cannot feed by ourselves. But now we have a parallel position, and then I can sit there even as a Korean, and I can have a lecture here for the Australian people. You guys already have a 100 history, but. So I realized again, I'm so proud of my country, Korea, and then also I also keep doing and I keep working as a partner or a collaborator to do something for the space, and then not only for the space but also for our own planet Earth. Thank you.
There's an enormous amount to be proud in that, Dr. Yi. I think it's wonderful. Following Dr. Yi, we now have Dr. Daniel Bayliss. Dr. Bayliss is an astronomer at Mt Stromlo Observatory. His research focuses on, here's my notes, detecting and studying extrasolar planets, planets that orbit stars in other galaxies other than in our galaxy, other than the Sun. Daniel.
Thank you. So when I tell people I'm an astronomer, I usually get one of three responses. It's either you look at stars, can you tell my future, or have you been into space? So the answers are yes, no, and I wish. And I think this is probably about as close as I'm going to get to going into space, is to sit with someone who's been into space. So it's a great honour to be here on a panel with Dr. Yi. So what I want to talk about in the brief time I've got is just some of the astronomical scales that are involved with spaceflight and with my research. And as Dr. Yi touched on, the International Space Station is really only just above the Earth. So here I've got a globe to represent Earth, and I was wondering if people would guess how far up the space station is. Okay, so put up your hand if you think it's up here. Okay, so I'll come in and just raise your hand when you think I'm at about the level where the space station is. Out here?
More.
Yeah.
Oh, already. More.
Yeah, there we go.
Almost.
Right down there. So you can see, even going into space, we're really only getting just above the Earth. And so all that energy that goes into firing that rocket up, and you only get that far above the globe there. Of course, mankind's been further than that. we've been to the moon. So for the moon, I've got a scale moon here. It may look like a cricket ball, but this is really the moon, okay? And that's the right scale of size between the Earth and the moon. Now I need a volunteer for someone who's going to be the moon. Would anyone like to be the moon for me? All right. Now, unfortunately, Addy does astronomy, so
But I don't know.
he might have a little bit of an idea. So I want Addy to stand at the right distance where the moon is in orbit around the Earth.
I'm
Okay?
feeling I have to go out of the room.
Okay. So who, do you think Addy's got it right that far away? Up the stairs, Addy. Up the stairs. Further.
Wow.
So right in that corner, that's about where the moon is compared to the Earth. Okay? So it's a long way away, isn't it? Humans have been that far, but it took us... It took 3 days to get there. So what about what I study? Can we turn the lights down a bit?
Yeah.
Okay, thanks, Charlie. So I study extrasolar planets. And by definition, that means a planet that's going around another star. And we're actively looking for planets such that this is an artist impression of this planet going around another star. We're actively looking for these at the moment. But they're a long way away. And if I gave someone an extrasolar planet and asked them to walk away, they'd have to walk away for a very, very long time. Unfortunately, it's out of the realm of this scale. If we could travel to one of these planets as fast as we travel to the moon, it would take a very, very long time, okay? So does anyone want to guess how long it would take to get to this closest extrasolar planet if you're traveling as fast as we did travel to the moon? Months? Years? 10 years? Any advancements? Longer than 10 years?
Yeah.
1,000 years? 129 million years, okay? So even the closest planet that I study is a very, very long way away. And so when we talk about the difference between going to the space station and the things that Charlie and I study, you can see there's a great difference. And that's the closest. Most of them are much further away than that. So you might wonder, how do we study things that are that far away? And I'm just going to give you show you two methods how we study these things. So the first is to try to find a planet around a star. If you monitor the star carefully, you can actually see it wobbling. That's because as the planet goes around, it pulls on the star gravitationally, and so the star wobbles. So if you carefully monitor the light coming from the star, you'll see that wobble, and you can infer there's a planet there. Okay? So I should point out, these planets at the moment are too difficult for us to just take a photograph of. They're so far away and they're so close to their star that it's very difficult to image. But we can see the stars wobbling sometimes, and that tells us there's a planet going around. And the other way to do it is look for the star to dim slightly, and this is what I do in my research. So you monitor the star very carefully, and every so often, this is brightness here, the brightness will drop a little bit. It's quite a small change, it's about 1% for this type of system. And when it dims like that, and it does it every 3 days or 4 days, then you know you've got a planet going in front of that star every 3 days or every 4 days. And so this is the type of research I do, detecting these planets by indirect means, even though they're so far away. And you might think this would be incredibly hard, and it is, but you can actually do it on reasonably small telescopes. So these are the telescopes that we've set up in a project called HAT South, looking for planets going around other stars. And you can see from the silhouette here that these telescopes are only about that big by that big. Okay, so they're not much bigger than people's amateur astronomers' telescopes, and yet we can find planets going around other stars. So this is the kind of research I do. You can see it would be almost impossible for us to ever fly to these planets, unfortunately, but by using techniques like this, we can detect them and we can study them. Thank you.
Despite the fact that I want to ask questions of both of them now, we're going to have to hold the questions until we finish with all of our panelists, and then we'll continue. Thank you, Daniel. Next up, Associate Professor Charlie Lineweaver. Charlie Lineweaver is Associate Professor at the Planetary Science Institute here at the ANU. His research involves the analysis of the distribution of exoplanets, the cosmic microwave background radiation, and cosmological prerequisites for the formation of terrestrial planets and life. Charlie.
Okay, thank you. Well, thank you very much. So as a scientist, I'd like to start out by disagreeing with Daniel, because Daniel said that he doesn't think we'll ever get there, and I'm much more optimistic than that. I think Alpha Centauri being 4.2 or 3 light years away, I think that almost every star out there has some type of planet around them, and I'm looking forward to the first interstellar mission. I'm not sure when that will be. NASA or anyone else hasn't built one yet, but I suspect in the next 10 years that the public will be interested in interstellar flight. I just thought I'd put in my own plug for an optimistic hope in that direction. All right, so this is now have a look at this. This is my, Addie, can you raise your hand? About an hour ago, I asked Addie, can you show me what you can do with Google Earth? And I just wanted to show you a few places that you're familiar with. This is the Capitol. And now you probably drove from the Capitol down Canberra Avenue, and then you came out to Stromlo, which is right there. And that's where we are. Here we are in this building right there. So we're sitting right there. And then, now if you back out from Stromlo, and then, where are we going now, Eddie? We're going to KARI. We're going to back. Okay, yes, there's New South Wales and Australia, and there's Tasmania here, New Zealand here, and then Antarctica here. And then you rotate the globe, and you can see. And I asked Dr. E if we are in the same time zone as Korea. But anyway, this is where KARI is. I bet you're familiar. There's a beautiful forest down here, it looks like. Anyway, you go down here, and that, I guess, is where you work? You work here?
Just neighbor. Yeah.
Just neighbor, okay. All right, and then we're backing out. So that was Korea. And we'll back out a little bit, and we'll see the whole Earth again. And I love Google Earth because it helps you navigate. It gives you a feeling for how small the Earth is and all the tiny places in it, and so you can zoom in. And look at this Korean Peninsula, China, Japan here. And then I wanted to show you, in 1768, there was this map. Now notice that Korea was still divided, the 38th parallel, even back, even back in 1768. This is a map that Bougainville in 1768 had on board, and you can see where Australia was.
Oh, it took close.
They didn't know about this. They knew about New Zealand, and this side, this is New Holland, but over here was still unexplored. But they knew about Korea and Japan. And anyway, I just thought that this was an explorer 300 years ago, and what we're doing today is similar. We have much better maps of the Earth, for example. And here's a map with Korea on it, and underneath the clouds, and Australia down here with lots of sunshine. So if we back out a little bit, we have been to the moon, and there's Australia, seen from the moon. Now there's one issue about planets. Now I guess some of the things we're doing now is sending lots of missions to Mars. No person has been there yet. But there's something very interesting about these 3 Earth-like planets, terrestrial planets, rocky planets, is one has water and the others don't. And we're trying to figure out why. Notice that Venus is about the same size as the Earth. It had a gravitational field strong enough to hold on to water, but it was lost. Now Mars, let's take a close-up look of Mars. And when this is a topographic map of Mars and of the whole planet, and you can see all kinds of structure here. And if you zoom in on this region here, you can see that it looks an awful lot like there's been a lot of water flowing through here. You can see water channels that have gone through and washed to the northern pole where we have lowland area. This is what it looks like close up. These are also non-manned missions. I would like to go to Mars, but I guess they're going to have maybe some one-way missions to Mars I could volunteer for in about 20 years. Now, this is a star field, and the sun is a star. It's it's more massive than 95% of all stars. And we live in a galaxy something like this, and Earth is about there, and the sun is about there. And then if we back up, this is the Hubble Deep Field, and each one of these images is a galaxy. So our whole galaxy that I showed you here is one of these dots on this image. So for example, from an extraterrestrial point of view, we're saying, oh, there's a galaxy. There's a galaxy with about 100 billion stars in it. Now, Also, if we go on the larger scale, one thing that I study cosmology, I love cosmology because on the largest scales will always be lost. Just like in the map of Bougainville in 1768, he didn't know where he was. He said, oh, is there a continent here? Is there land? And in many ways in cosmology, we don't know where we are. We have an idea about a multiverse. In other words, our universe might not be the only universe. There may be other universes that are connected to our universe. So here we are, here's our observable universe on a larger universe, which has a daughter universe and a mother universe connected in some way that we don't fully understand. But if somebody says this to you, you should not say that's crazy. Science doesn't suggest that's the case, because there are vague or suggestive indications that this is a real picture of what we should imagine the universe to be on an even larger scale that we haven't really explored yet. In other words, it's not an illegitimate pipe dream. This is something that is supported by our best knowledge about how universes get started. Now, so the question, where are we? It's an interesting one. So here we are in the moon, and we're a star, and we're in a galaxy, and we're in hundreds of billions of galaxies, and then here on the largest scale will always be lost. And I think that's the wonderful thing about cosmology, because we're always studying the largest scales and we're always lost. You know, as Einstein said, if we knew what we were doing, we wouldn't call it research. I did want to say that we have some understanding of how planetary systems form. We look at there are many places where in the galaxy where stars are forming and planets are forming with them. Now, our understanding of how a planetary system forms is like this. There's some type of proto-sun here with a bunch of hydrogen and helium gas. It's very hot here. It's cool here. Here's where you can have ice. Here's where water turns into water vapor. And so you clear this area of volatiles. This is where you have hydrogen and the volatiles. The result is that anything that's here is like the Earth. It's mostly made out of rock. Anything that's out here is mostly made out of gas or volatiles and water. These is called Jupiter and Saturn are called the gaseous planets. Uranus and Neptune are more like water planets. And then anything like the Earth, Mars, Venus, Mercury are rocky planets. So here's some data. I wanted to show you one slide of data. I know it's complicated, but on the x-axis is period. On the y-axis is mass in units of Jupiter's mass. Now here is our solar system in red. Notice that there's the Earth, there's Venus, they're about the same size. Mars is much lighter than Earth, and so is Mercury. Here's Jupiter, 300 times more heavy than the Earth. There's Saturn, Uranus, and Neptune. So that's where the period of the planets in our solar system are, and here's where their masses are. The region of this plot that we're able to detect, that we're able to look at, is right up here. Here are the various techniques, the radial velocity technique, the transit technique that Daniel talked about. And if it's a round symbol, then the planet, the exoplanet, a planet around another star, has been detected with a radial velocity technique that Daniel described. The transit technique is the triangular symbol. Then there's direct imaging. There are a few exoplanets that have been directly imaged. They're hot enough and young enough and far enough away from their host stars so that we can image them on the sky with very high resolution imaging detection techniques. Microlensing is another technique, and pulsar timing. Those are right here, and right here. What we're trying to do is use these techniques to find something here. Notice that we're already starting to find planets around Jupiter's mass and Jupiter's orbital period. But we're not yet here. There is a new satellite that Daniel didn't mention called the Kepler satellite, and it is a transit. It's using the transit technique, and for the first time, we should be able to see something that approaches Earth mass planet around a sun-like star. That's something that was one of the holy grails of this profession, is trying to find Earth-like planets around sun-like stars, and then that have water on them, and then we try to ask the question, is there life there? Should we expect life there? And then we get into hand-waving, and but we're trying to find out, to help us understand this, we're trying to understand the origin of life on this planet. How did life get started? How long ago? Do you absolutely need water? Do you have to have DNA or not? What kind of amino acids are you going to use? This is something called astrobiology, and we're starting to put together information that helps us understand how life got started on this planet. Then what we have to do is separate the quirky information from the fundamental information, and use that fundamental information to make our best guesses about whether life has evolved on other terrestrial planets in the universe. And the Earth is the cradle of mankind, but one does not live in the cradle forever. And so I'm hoping sometime in the next decade or two, we're going to have an interstellar mission. I'm not sure if it'll be manned or not, probably not, but to get a closer look at some of these exoplanets, particularly around Alpha Centauri, because if we really destroy this one, World War III, 4, and 5, or there's some type of viruses that wipes out, if we start to really destroy this planet, we need an escape hatch. And maybe the planet around Alpha Centauri is one. I'm not quite sure, but it would be good science to find out. Thank you very much.
Thank you very much to all of our panelists. I'd like to open the floor up for questions. So, would anyone like to get started? I was going to firstly just say to Charlie, it could actually be not a manned mission, but a woman's mission.
Yes.
A
one-way man or a one-way woman mission.
Yeah.
Right. Would you volunteer for a one-way mission to Mars?
Mars is too close to go to the one way, actually. Just
No, it's
500 go and back, so we'd better get back. But Interstellar.
But it's much more expensive to get back.
But it's it will be really boring after 250 days later. And then what do you want to do?
It only takes 6 months to get to Mars, right?
Yeah, you're right.
So 6 months, you can watch TV, a lot of DVDs.
If there is, and then if I will not alone with some other people, so I will be there one-way ticket, but alone I don't know. But if I can go further, maybe it will take 10 years more to get there. I will go there one way. Yeah. But my mom hates that. Yeah, whenever I answer yes, and my mom hates that. You shouldn't answer like that.
Well, was it your mom who inspired you to become an astronaut, or?
My mom told me if you don't want to go, frankly tell me, and then I will tell to the president. Because my mom feels like I'm so scared, but I cannot tell because I was picked. But it was totally different. I really, really want to go there.
That's back there.
And how scared were you when you're on the launch pad just about to take off?
What?
How scared
How
nervous
scared?
were you
Ah.
when you're actually on the launch pad?
Frankly speaking, I cannot be scared at all. Because we were so busy with our own job. So if you concentrate on your own work, and then you cannot be scared at all. There's no energy, no kind of time to be scared.
But when you feel the energy of the rocket and the G-force, do you feel nervous then?
No, we were excited. Because we should go inside the rocket 2 or 3 hours before. And then should be strapped like that. So after 1 or 2 hours later, we were confused with whether it's a training or real launch. Because it's totally same with the simulator. Because there's nothing through the window because all the things are covered with a nose fairing, so you couldn't see anything.
So what's covered? The windows are covered.
Yeah, window covered with a nose fairing.
Oh.
Because we are inside of the rocket. So yeah, even we talked to each other with the crew, and then is here Moscow or Kazakhstan? Because we feel like it's training. And even Russian people are very smart. And then when we were inside of the rocket, they bring the instructors to the Kazakhstan, and then we can communicate with a familiar voice. And we always have the same instructors have a simulation, and then even he came to the Kazakhstan, and then they tell me the mission. So we feel like really simulation. So it's not scared. And then right after launch, and then we realize that it's real. So we yelling up, "Oh my God, it's real!" So
Wait, you're telling me you're kept in the dark about whether you're going to really launch or not?
not that we have a light inside.
Well, what about re-entry then? How does that go?
I couldn't tell you normal feeling of the reentry because I had a little abnormal reentry. We had some problem with the separation, so we should have a ballistic reentry. So we should land on the 500 kilometer from the pointed area. So we were lost for a while. So my mom thought I was dead because we didn't have any communication at all. So after 30 minutes, finally we could have a signal, and then we can talk with the mission control center, and then they came to our side, and then they saved us. But it was also really, really unique experience because even the Russian cosmonaut, they already have a several flight experience, but they couldn't have those kind of abnormal situation at all. But only with the one flight, only with a 10-day stay, I have really unique experience. And also it's a great chance to prove that I did my best during the training because we had a training for the abnormal situation, but we did a great job. So all the instructors said that, yes, you also prepare for the abnormal situation. So I think as an astronaut, those kind of abnormal situation is a great chance to prove that we are not that bad astronaut.
What was the hardest thing about being in space?
Hardest thing is, most of all, I cannot accept that we can fly like a Peter Pan. So it's really fantastic. And another thing is, as you know already, we are almost here. So when we see through the window the stars, almost same formation, almost same constellation, almost same size. But we don't have an atmosphere, so we don't have any diffraction. So we could see the color of the stars. Whenever you go outside at the night, and then whenever you see the stars, all are yellow because of the diffraction. But you go up to the station, even though it's the same constellation, but each star has a different color. And then some things are reddish, some things are bluish, some things are greenish. So always I wondered about and I curious about, my science teacher taught me about star. Because when I was in middle school, my science teacher told me if star has a high temperature, it will be blue. If star has a low temperature, it will be red. But I've never seen red star at all at the sky. All are red and all are yellow. But when I go up, I could feel that. Some things are red and some things are green, so it's really fantastic. You should go there.
I think just beyond the amount that everyone in the room was jealous of you, you've added to it all of these. How much they're jealous of you.
And I've got to say, if you get time to look at the stars in Australia, you'll see some red ones and some blue ones. Maybe the skies are a bit clearer than they are in Korea.
Okay.
How many astronauts do we have up to now?
Up to now, for whole world? Actually, some astronauts are already retired, but we can count the person who've been in space all the way from the Gagarin. And I was 475th. And then several months ago, we have 500. Nowadays, maybe 500 or a little more than.
That's like the number of exoplanets.
Well, there's been a call to start naming the exoplanets with names a little bit more graspable than KC 512, and perhaps we should start naming them after our astronauts.
Yeah, that's a very good suggestion.
Yeah, good.
So you
How
can
far do you have to go out to be considered astronaut?
By the Wikipedia, we don't have to go to the space because by the dictionary, astronaut is the person who already have a training for going to the space. So those kind of count, maybe astronaut should be around 1,000. But we could say the space above the around 100 kilometers. But by the law, different country has a different standard. So some country claim that above the 90 kilometers is the space. And then some countries said that above the 200 kilometers because sometimes we have some kind of dispute or fight each other because of the satellite crushing or something. So it's very important definition until what point we could tell the space or not. Because if above the 100 kilometers, we can apply the space law. But up below there, we should apply aero kind of airplane or aero law or something. So it's a very sensitive definition.
So you mentioned Wikipedia, and were you able to Wikipedia in space? You have Google, you have internet connections, and you're able to define an astronaut while you were flying around the Earth?
Actually, until several months ago, we couldn't have internet exactly. We can have a communicate, and we can access some kind of special network, but we couldn't have exactly same with the internet of the Earth. But as I know, NASA constructs some kind of network system, and then they can do internet freely. But as a foreign astronaut, to do that, you should pay whole really big bunch of money. Even I cannot use a telephone because each minute has a really expensive. So for the Russian or American astronaut, they can feel free to use the telephone anytime. It's a kind of psychological support because they should stay there more than 6 months.
But you didn't have that.
But I'm kind of contractor. I'm kind of visitor. So I should pay exact amount of the cost.
It's like a really rigid share house. You have to work out.
But it's reasonable because Russian people construct the station for the American people. Now American people set up the system with a really big bunch of the money, and then they have service for their own citizens. So yeah.
But I would have thought they treated their visitors better than that.
But one really fantastic privilege is like that, and then when I get back to the Earth after 1 or 2 years later, at the end of the year, and we had a party with my family members, and I got a phone call from somewhere, but I don't know from where. But from the space station, a friend of mine called me. Happy New Year! Where are you? I'm stationed. Oh my God! So it's really. But it was so funny. My mom and daddy, and then some friends of my parents, surprised with a phone call from the station. But my sister, she doesn't have any experience with the international collaboration or any experience to go to the foreign country at all. So she told me, I don't care from where and then from station, but I was surprised you talk with somebody in English.
Oh boy.
There's another question. What does the air smell like on that space station?
Totally same with our laboratory. Yeah, because there's so many fans and there's so many machines. So just like my laboratory. So as an engineer, totally same. Even only different thing is zero gravity. But some tourists say there's some unique kind of taste or smell like that, but maybe they are always in the office and they are millionaire or something, so they feel it differently. But as a pilot or engineers, we are very accustomed to have those big noise and then those bunch of machines. So for me, it was not that different.
Could I just ask on that, not about the special scent for the tourists, but the machines and the experiments. What experiments were you working on up there?
Not only for the astronaut, but also for the experiment, we had a competition, we had a selection process. So even before start astronaut selection process, they have a announcement to every research institute, every national laboratory, every university, and then if you have any idea to have a space experiment, you can propose. So more than 100 proposal government got, and then they examine with the committee, and then they pick the 18 experiments. Now among the 18 experiments, 4 is for the kids, education, and then 14 is from the every field because to make a fair. So from the biology, from electrical, from mechanical, from chemistry, and then from physics. So to make fair share, so we should pick every field. Yeah. So I'm not the person who planned the experiment. I'm just the person who do experiment by their manual. So I'm a kind of like robot in harsh place.
So you might want to go back again, right?
Hopefully, but it depends on the government
If there's
policy.
anything, what makes you feel to go back? And if there is anything,
Yeah,
what
yeah.
makes you feel not to go back? Can you come up with any,
I would never think about I'd better not go again. Never, ever. I really always miss the time I've been in space. So whenever, whatever I could have a chance, will be on the rocket. Yeah. So even thinking about to steal the seat of the Russian people.
Okay, this one's for Charlie. So, you say that you're optimistic about human spaceflight to other stars, and yet it's kind of hard to argue with the numbers that Daniel gave us. It says that it'll take us more than 100 million years to get to the nearest planet. So, are there any advanced spaceflight concepts currently on the drawing board somewhere that could get us there quicker?
There are, but they're usually done by some engineers who are very hopeful. Daniel's calculation for 130 million years, I think, was based on Apollo speeds.
Right.
And I think that we can do a lot better than that, maybe up to 1/10 the speed of light, and that would probably reduce the number by a factor of 10 or something, Daniel, do you know?
More than that.
More than that. So that's, and I wasn't necessarily talking about human, I was talking about rockets going there with very good webcams and robots, but not necessarily humans.
So yeah, okay, got it. It's still getting us there in 10 million years.
Yeah, still.
You're a short-term thinker, are you?
We can expand our life.
That's right.
Hi, I'm not a scientist at all, and I know nothing about science, but because I'm interested in your story, I came here and I learned about science, and it's really great. So I guess my question is, I know in South Korea you became like a popular celebrity overnight, kind of a rock star scientist, and I was wondering if you can tell me anything about the impact that you, as a woman and a Korean going to space, had on space research in South Korea, or on public interest in space research and this kind of thing.
It was a really big impact. Actually, if I were willing to be an actress or a singer or something, I could be prepared for those kind of impact, because I could see every singers and every actress, and they could know how to react and how to work with the public. But in my case, 1 year before I should move to Russia, and at the time I couldn't access Korea very well because we don't have good internet, we don't have good communication, and I was almost isolated in the military base of Russia. And when I picked last two, I was not that famous because Korean people cannot recognize well about space program until that time. But right after my launch, I could be on the television every night with flying. So at the time, all the Korean people could know my name and face and my activity, and then I'm an astronaut. So one day, we have a very big awards among the celebrities, among the actress or actor or something like that, and then one guy got a top, and then he has some kind of comment in front of the mic. Maybe astronaut Soyeon could feel like me because I got a top. So one friend of mine called me and he talked about you in front of the TV. So I didn't believe it at all. I know him, but he shouldn't know me because I'm just a Soyeon and then I'm just an ordinary people. So in that point of view, and then I couldn't realize how famous I am. But after all program, and then I should get back to the Korea, and then in the airport, open the gate, and then saw a bunch of public and then press and then people in front of me and take a photo. So I thought, I was sure that maybe somebody behind me, a very famous celebrity. So what's that? Oh my God, I'm so unlucky. I should go to my home and I should meet my parents, but I cannot find them at all. But they look at me and ask something, and then some journalists raise a hand and they look at here, and then how do you feel like that? For me? And my mom and daddy stand there with a flower, but they think like that. So finally I realized something happened to me. So after that, whole my life is totally changed. Even though I'm not changed at all, but all the things around me was changed, and all the people treat me as a very famous people, even though I'm just 29 years old at the time, and then just a woman, and then just a female engineering school students. So it was really hard to treat and hard to handle. And then even I went to the public bath, and then some girls come to me and then please autograph, even on the bathtub. And sometimes I went to the supermarket and then I have the tray, and then some people come to me and then please, and then it was a really big shock. So I don't know how to handle it, but after time, as time goes by, I could be accustomed to do that. And then sometimes I feel so happy whenever I met the small girls, and then, you know, engineering field, there's a few women. So they always feel complex, and then they always feel like stressful among the guys. But sometimes they told me, and then you are hope of Earth because you made it among the whole bunch of guys. So at the time I feel so responsible to do something for them. And then one day I got a letter from the small kids, and then he said to me, even though you went to the space by the Russian spacecraft in this time, but wait a while, because I will be a scientist and I will make our own rocket, and you should be inside again. Yeah, it's really inspiring. It's really, really inspiring. So because of those kind of things, even though my life becomes so tough, I should handle it, I should face it. Yeah.
Is that?
Oh, thanks. One for Charlie and Daniel.
exoplanets around binary stars. Have we found any or many, and how do they fit in the rocky, gassy model, if that's possible?
So I think there's been one found by looking at the timing between the eclipses in the binary system. So this is a system where you have two stars very, very close together, and they orbit each other very quickly, and then you can have a planet going around those two stars. And in fact, when we think about stars, most of the time we think of a star like our own sun, but in the galaxy actually there's a huge number, we're not sure of exactly percentages, but perhaps half of the stars are binaries, perhaps even more than half. So when we look out in the night sky, those things that look like a single star may in fact be two stars in a very close orbit. They can be quite difficult to find though, because the techniques that I showed you don't work very well for those type of systems. To look at the stars wobbling, if there's two of them going around in a very close orbit, they're wobbling a lot because of each other. And so you're looking for another signal on top of that. That's quite difficult. And in terms of eclipsing, that can be difficult as well, because the light is constantly varying because they're orbiting each other. So it's quite hard.
Well, if you've only found one so far, it's
yeah. So 1 out of 500. Yeah.
Well, some binary stars are close, and other binary stars are very far apart. And the habitable zone around, let's say the habitable zone around this star is this big. If they're this far apart, then you can have planets around this star, you can have planets around this star. If they get this close, then you can't. Then you might have a habitable zone that's circumbinary, going around both of them. So there are all kinds of combinations. I don't think, my suspicion is that if you're very close, of course you're going to disrupt the planetary orbits. But if you're far away, then you can have close orbiting planets, but not far orbiting planets, essentially.
So on that graph you put up earlier, a lot of the planets that have been detected were groups along the period axis. Why is it easier to find planets with that particular period?
The ones in the upper left of the plot were the most massive ones and the ones with the shortest orbits. And that's because for example, you can imagine that there's a star here and a planet is very close to that star. If it's very close, there's a higher likelihood that you will just see I mean, there's another planet going around like this, and it's passing in front of the disk. If you're perfectly aligned, but if this planet were this far away, then you have to be even more finely, just exactly to get it to transit in front. So the transit technique is very sensitive to planets that have small orbits, but not so for ones that are out here. The alignment is just too hard to get. So that would explain why the transit one is sensitive to small periods. The Doppler shift, also, if you have a planet here, they're going around like this. And so you can see the radial velocity going like that. But if the planet is out here, then the radial velocity is very slow. And you have to wait 20 or 30 or 40 years for it to see it go one cycle. And then we haven't waited that long.
Can I just flesh out on that? You mentioned previously, well, you might have talked about it as well, Dan, the suspicion that most stars have planets. Would you say that that's probably the case?
Well, I've been saying that for about 5 years, but Daniel, why don't you tell me why I'm wrong?
We're still waiting to find that out.
Yeah.
So hopefully we'll know in the next few years with the Kepler satellite, like Charlie talked about, because that's sensitive to finding planets like Earth. And I hope Charlie's right. I hope there's lots of Earths in the galaxy. But that's only a hope. I don't know.
Do you hope there are lots of aliens in the galaxy? You didn't see any aliens when you were out in outer space.
You see, it's too close.
Sometimes astronauts report when they go up into outer space and look down at the Earth, they see, oh, this is a whole Earth and there are no national boundaries like you see on that map. There are different colors for every country.
Yeah,
and
right.
Obviously, you don't see that from outer space.
Yeah, right. My first interview was like that, and then a person said that, did you see the Korean Peninsula through the window? Yes, I did, but there's no border between North and South Korea.
Did that change your way of looking at the world and say, hey, we're all in this together? Or you're obviously sponsored by one country to go up there, so at the one time you're nationalistic, but you're also seeing the world from a trans-nationalistic point of view.
Yeah, right. I realized how small my country is, because it takes 90 minutes to go on one round. And as I told you before, it takes 20 minutes to go over to the Russia, and then it takes 10 minutes to go over to the China, and then I'm waiting for the Korea actually, because we have a laptop, and then that laptop keep telling us where we are. So for 20 minutes, I'm tired of hearing the lassi, 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 and then after 10 minutes, gittai. Gittai is in Russian, China. And finally they say, KARI! So I run to the window and I open the window, but already Pacific.
Japan.
Yeah, and then even they cannot call Japan because we just pass by. And then sometimes they call the China and then Japan. Just skip the Korea. So at that time I realized how small our country it is, and then how small I am either, because when I was in Korea, I think Korea is too big for me. And whenever I have a business trip, it takes 3 or 4 hours, and then I should spend the whole day to go somewhere. So, oh my God, it's too small. I'm too small. And then one interesting thing is, whenever we have some kind of shooting or dotting, and then always a small object is a high point. So maybe Korea is also small, and then how difficult to be born on the Korea. I got a lottery. Yeah.
Okay, just one final question.
I was wondering, how long will it take until we have the technology to directly image Earth-sized planets, say up to 100 light years?
I would guess about 25, 30 years. I guess, Daniel, would you agree with it? What do you think? They're working on they're working on what's called an interferometry, a nulling interferometer. So what you need is a space-based two telescopes that are using interferometry to null out the very, very bright star to get that close. Right now we can already image planets that are very far away from their host stars, and they have to be very young because they're glowing with the heat of accretion. But that's not what the Earth would be doing, and so you have to get very better technology. I guess 30 years. Daniel, you think I'm unrealistic?
I think it'll be longer, but like these things, the amount of time they take, I think depends on the amount of money and energy humans decide to invest in it. Because you saw that we went to the moon, but that was a long time ago and no one's been back, and that's not because of the technology, it's because of the money and effort that's gone into that. So it really depends on how focused people are to try to do this work, and perhaps if we focused a lot of money and energy on it, it would be as short as Charlie says, but I suspect it'll be much longer.
You can buy up to maybe 100 years there.
Oh yeah, at least.
And if you gather the whole scientist and then make a big prison, and then you cannot come out after making that, with giving enough money, it's possible.
Well, I think 10 years, if that's 5 years. How much money are we talking about? No, I think it's possible because a lot of people want to know the answer to that question. How common are Earth-like planets? How common are planets with water on them? And how common is life elsewhere? Those are big questions people want to know the answer to. I don't think they're going to get tired of the answer to that question that we come up with. And so I think as we learn more and more, there will be more and more money going into that direction because it is such a compelling question.
It depends on the motivation, I think. So I always heard from the Russian and American experts about space program. They said, without Cold War, we couldn't make Apollo, we couldn't make space station at all, because they were so competitive, and then they don't think about how much they need, and then just push the money and then make it to compete each other. So they couldn't make it. So maybe those kind of thing also. If you have a really big, huge driving force, we can make it in 10 years. But if there's no interest from the public and there's no driving force, maybe forever.
So we need a Cold War again.
I've been tossing up in my mind how I wanted to wrap it up, and I was thinking all of these humbling thoughts that they've been going through. But the one that stuck in my mind is the scientist prison, where we all try and solve the problem so we can all get out to the planet. On that note, I'd like to thank our panelists for a wonderful and fascinating talk.